Hello friends, once again welcome to our this new video. So this is the video number 21 based on the topic solutions. So in this video we are going to learn the very simple aspect, that is the modification of the expressions of the colligative properties for the solutions of the electrolytes. So in the preceding videos we have already studied how the various equations or expressions are obtained for the non-electrolytes. That is what? From the Raoult's law, we have studied how the lowering of vapor pressure is related to the mole fraction of the solute. So from that we can easily determine the expression or the equation of the lowering of vapor pressure. So that is like this. So in this case, now see, for the solutions of the electrolytes, so all that the equations which we have already studied for the solutions of the non-electrolytes, that can be modified by using the One-Top's factor. So in this case there is just change is that the One-Top's factor I is added with these equations. So that is what the lowering of vapor pressure, that is delta P is equal to I into P10 x2, where that is the vapor pressure of the pure solvent. P10 is the vapor pressure of pure solvent, that is given in the Raoult's law. X2 is the mole fraction of the solute. So how the lowering of vapor pressure is related to this? Then the mole fraction of solute, that is X2, again is given by the formula, that is N2 upon N1 plus N2, by substituting the values of N1 and N2, that is the weight of solute divided by its molar mass, weight of solvent divided by its molar mass of that solvent. By rearranging we will get the such type of equation. So only change is there. So for this watch all the preceding videos in order to prepare how these equations are obtained for the lowering of vapor pressure, then for the elevation of boiling point. Similarly, just One-Top's factor is added there in the equation like this. There is no any other change is there. Then similarly for the diffraction in freezing point, so again for the osmotic pressure the equation becomes like this. So that is what we have to use all these equations at the time of solving the numericals. Just the modification by adding the One-Top's factor, the equations are modified, that is equations which are already derived for the solutions of the non-electrolytes, and now these equations are applicable for the solutions of the electrolytes. With this we will study the last one more article from this topic, that is what? How the One-Top's factor is related to the degree of dissociation. How the One-Top's factor is related to the degree of dissociation. Before that I will revise in brief what is the degree of dissociation, then how the equation for the Ostwald's dilution law for the weak electrolytes is obtained, and finally we will study the One-Top's relationship, the One-Top factor and the degree of dissociation. Now see, before studying the relation between One-Top's factor and the degree of dissociation, I will revise in brief regarding to the degree of dissociation. So this is the aspect from the topic ionic equilibria. So what is this degree of dissociation? So this is denoted by the symbol alpha, and this is nothing but the fraction of number of moles of an electrolyte that dissociated or ionized at the equilibrium stage. Try to understand what is the degree of dissociation. It is defined as the fraction of the total number of moles that can be ionized or dissociated at the equilibrium stage. See here, that is the equilibrium constant K can be derived with the help of the Ostwald's dilution law. That is what the dissociation constant K can be obtained or derived by taking the help of Ostwald's dilution law. So for that is how the dissociation reaction for a weak electrolyte can be returned. So see here, let us consider AB and weak electrolyte, that is represented with the help of the symbol AB. Let us AB be the weak electrolyte. Then its dissociation reaction and the equilibrium concentrations are given like this. So now see, what is that? Let us consider 1 mole of an weak electrolyte. 1 mole of an weak electrolyte AB is dissolved so as to produce the A plus and B minus ions. So in this case, when 1 mole of an weak electrolyte is considered to be dissolved in V decimeters cube of solution or V liters of solution, and alpha be the degree of dissociation. Alpha be the degree of dissociation, that is the fraction at the equilibrium stage, or the fraction of the number of moles of an weak electrolyte that ionized or dissociated at the equilibrium stage at that time. Now see, what is the consideration? Listen once more. If 1 mole of an weak electrolyte AB is dissolved in V decimeters cube of solution and alpha be the degree of dissociation, at that time the dissociation reaction of this weak electrolyte and its equilibrium concentrations can be given like this. See here, AB gives A plus B minus. Initial number of moles AB is 1 at the beginning before the reaction. At that time A plus 0, B minus 0. Then at equilibrium stage, alpha is the degree of dissociation. That's the number of moles at equilibrium stage remaining of AB 1 minus alpha and A plus alpha alpha, because this is the degree of dissociation at the equilibrium stage. So at equilibrium stage we will get this such type of concentration. Then concentrations in moles per liter, 1 minus alpha upon V, alpha upon V, alpha upon V. That is what. Then now the dissociation constant K can be written by applying the law of mass action to the dissociation reaction. That is all. Simple. So we have already studied this law of mass action, that is in the videos of 11th standard chemical equilibrium. So once again look at that, how that is these concentrations and the law of mass action, how this can be explained there. Then see here, the K can be written, dissociation constant K for the weak electrolyte is written like this: molar concentration. So molar concentration of A plus into molar concentration of B minus upon the molar concentration of A. So simply that can be written, the concentrations of the products are written here above and the concentrations of the molar concentrations of the AB are written like this at the denominator. So we will get dissociation constant. Now this is simple thing. Now by substituting the values of A plus B minus and AB from this, look at this, we can write that is A plus, value of the molar concentration of A plus is alpha upon V, value of B minus, molar concentration of B minus is alpha upon V, and the value of AB is 1 minus alpha upon V. From this we can write like this. Now see here, that is all. This can be written alpha square upon V into V upon 1 minus alpha. So 1 V get cancelled here. So we will get K is equal to alpha square upon V 1 minus alpha. But 1 minus alpha is very small, and that's why it can be negligible or neglected. And we will get K is equal to alpha square upon V, or alpha square is equal to K into V. Alpha square is equal to K into V, or from this we can write K is the constant. That's why alpha is directly proportional to the square root of V. That is called a degree of dissociation is directly proportional to the square root of dilution, or 1 minus V. Instead of 1 minus V we can write C, that is the concentration. So K is equal to alpha square into C. Alpha square is equal to K upon C, or alpha is inversely proportional to under root of C. So that is according to the Ostwald's dilution law, that is the degree of dissociation is directly proportional to the square root of dilution or inversely proportional to the concentration of the solution. So we have to use this aspect in while deriving the relation between Van Hoff's factor and the degree of dissociation. That is the one of the important derivation we will study in the last video. Thank you.